So we're going to continue today with chapter 4. And the last thing that we did last time, we were starting to get into hazards. I went over the description over the 3 types of hazards that we encounter when implementing pipeline designs: the structural hazards, the data hazards, and the control hazards. So today we're going to start by taking a closer look at each one of those. So as I mentioned, the first one and the easiest to deal with is the structural hazards, which means that we have conflict in the use of a resource, of a hardware resource. For example, if we are addressing memory and we are using the memory for data, for the loads and stores, but also we are using the memory to store our program during the fetch cycle, that would create a conflict on that bus if we had a single bus. So the easiest thing is to split the bus and have a separate memory for instruction and a separate memory for data. And that's exactly what we're going to be doing. And that's what is done in modern processors, where the memory that is closest to the processor, in this case the level 1 cache, are split. This is what is called a Harvard memory organization, in which you duplicate the buses for data and instruction and you have separate memories. So those are easy to deal with. We just replicate the resources for structural hazards. Now let's talk about data hazards. And let's try to illustrate how that would come about. Let's say that you have these 2 instructions, an addition and a subtraction following it. And in the addition instruction, we are adding the contents of register 3 and register 2 and putting the results in register 1. Then, in the subtraction instruction following it, we are subtracting register 5 from register 1 and putting the result in register 4. Now, if we go through the 5 steps, or our 5 pipeline stages, we can see that in this clock cycle, we are fetching that instruction. Then here we are decoding the instruction and we are reading the registers that are involved in the instruction. So we are reading registers 2 and 3 in this clock cycle. Then in the next clock cycle, that's when we actually do the addition. Then this, for register type instructions, this cycle doesn't do anything. It just bypasses the memory, if you remember the mux, and it goes back. And then in this 5th clock cycle, that's when we write the results of the addition of registers 2 and 3, and we write it into register 1. Now let's look at what's happening for the subtraction instruction. Here we are fetching that instruction, and here is when we need to read the contents of registers 1 and 5 for that instruction. However, you can see that we are not writing to register 1 the result that we mean to get as a result of that sequence of instructions until 2 cycles later. So what we would read here, the contents of register 1 that we would read here, would not be the correct result or the correct source. So we have a data hazard. That's what we mean by a data hazard. And we're going to talk about how to fix that, given the obvious but clever observation that anything that we need, as long as it is in the processor somewhere here, we can get to. And we're going to have a mechanism for that. We're going to call forwarding, which means that if we are computing the result of the addition of registers 2 and 3 here, and we want it for this execution step, we don't have to wait until we write it. I mean, we will write it, but for the purposes of keeping the pipeline going, we don't have to wait until writing it. We can just grab it right from here and forward that to this stage. That's what we're going to call forwarding. So let's look at how we construct that. Now, we could wait, which is basically stalling the pipeline. We could wait for the clock cycle and then have it at that point. That would still would fix the issue. But again, as you implement more stall cycles or bubbles into the pipeline, you degrade the performance. So we don't want to do that. So I mean, because the more you have to insert stall cycles, you are essentially giving up the performance enhancements of implementing a pipeline design. So we're going to do what is called forwarding or bypassing. So you can see here that if we are executing here, we can forward that to the execution stage of the next instruction in the pipeline, even though we would write the register 2 cycles later. So that requires extra data steering and extra control, but that is fine. We can do that because we have the result inside the processor. So that mechanism, that technique is called forwarding. Now, sometimes we cannot use forwarding because we don't have what we want inside the processor, as it was in the case of the addition followed by a subtraction instruction. So let's look at that case when we're doing a load. Here, we are fetching that load instruction. We are reading the register involved, and decoding the instruction. So we would be reading register 2 over here and getting that immediate value to compute the address. And when we have the address, we would access the memory, and then we would write it here. We would write register 1 here. But let's say that the next instruction was subtracting register 5 from register 1, putting the result in register 4. So we need that result for executing the subtraction instruction, because that's what we're loading into register 1. But we don't have it until this point. And there is no choice because it wasn't inside the processor, it was in the memory. The data that we want, which eventually is going to make it to register 1, we didn't have it inside the processor. It's not being generated inside the processor as with the addition instruction that we saw before. We have to wait. And the sooner that we have that is at this point in time that we can then forward it to the execution cycle of the next instruction. But that still requires that we take a stall cycle in our pipeline implementation. So it isn't always that we can solve data hazards by forwarding. In the case of the ARM pipeline implementation that we're discussing, for a load instruction, we would have to take a stall cycle and still do forwarding to be able to minimize that performance degradation. Another thing that we can do to minimize hazards, data hazards, is to reorder code. And this is where the compiler, if the compiler has some understanding of the implementation, then it can help by reordering the code during compilation, which is called a static reordering. We'll see later that modern processors have dynamic scheduling of instructions, in which there is a prefetch buffer that fetches a sequence of instructions, not just an instruction, and looks at the dependencies. And in hardware, you can figure out these dependencies and you can reorder the code dynamically to minimize the penalty for data hazards. So we're going to see that in more advanced implementations later. But as a simple first example, let's look at this sequence over here. And we already established that a load is going to cost us 1 stall. And we're still going to do forwarding to reduce the stall, the number of stall cycles, but we cannot do any better than 1 single stall. So here we're loading into register 2, and then we're using register 2 as a source. So we know that we're going to have to stall before this addition. Then we're going to do a store over here, and we're going to have another load into register 4, and we're going to use register 4 for this addition. So we know that that's going to cost us another stall cycle. So in total, this code sequence is going to take 13 cycles. However, if we look at the dependencies here and we realize that we can move this load, the load over here, we can move this load up here and then insert it between the second load and the add. Essentially, we're using that stall cycle to execute that load, the load into register 4. But that's a useful instruction. So we are not really taking the stall penalty, because while we were waiting for the data to come from the first load into register 2 to be using the addition, we started performing this second load or third load in this code sequence. Then we can execute the addition with no problem. So at that point, the forwarding is going to work just fine, and we don't have to take that penalty. And we can then have this store over here. And then we can have another addition. So we have separated now this addition from this third load. And then we do our final store. So we're back to 11 cycles. Now, 13 versus 11 may not look like much, but what we try to look at when looking at performance improvements is at the percentage. Because at scale, over many millions of cycles, it becomes significant and meaningful. If we are looking at 13 cycles versus 11, that's almost 20%. And that's a big improvement performance-wise. Now let's look at the third type of hazards, and the control hazards, which is the most difficult to deal with. So we know that the branches determine the flow of control of our program. And after we have a branch, a conditional branch, the next instruction that we're going to fetch depends on the outcome of that branch. So if you want to keep the pipeline occupied, you won't know which is the right path to take. The instruction following the branch instruction immediately, which means that the branch was not taken, or the branch target instruction at the branch target address, meaning that the branch was taken. And if you look at our pipeline, when it's time for us to fetch that instruction, we're just decoding the branch instruction. So we don't even know at that point that is a branch instruction, let alone know if the branch is taken or not. So one solution is to look at this control hazard problem as a structural hazard, in the sense that we don't have the hardware to compute the branch outcome and the target and add that hardware to the instruction decode stage. So again, remember that anything that is a structural hazard, that is a lack of resources, a lack of hardware resources, or a competition for hardware resources, we can easily fix by duplicating hardware. That's the easiest thing to do, is duplication of hardware. So we can add that hardware to the instruction decode stage. And if we don't do that, then we would have to wait until the branch outcome is determined before fetching that next instruction. So let's say that we have just an instruction, any old instruction over here, an addition. Then we have a branch on 0. And here we have a register that we're going to check for 0. And then here we have our branch target label. And now we have the next instruction. Since we won't know the result of the branch, we will have to introduce a stall cycle. And that's what we're trying to avoid. Now the problem becomes exacerbated when we have longer pipelines, to the point that stall cycles become unacceptable. The pipeline of 5 stages that we're looking at by today's standards is very short. Normally you're looking at 9, 11, 13 stages type of pipeline. So if you just stall waiting for the outcome of the branch and you have to introduce 5 stall cycles, that becomes really unacceptable from a performance degradation perspective. So the idea then is to engage into designing algorithms and schemes to predict the outcome of the branch, and only stall if your prediction is wrong. And the idea is that if your prediction is good, the number of cycles in which you stall becomes minimal, and your performance degradation is minimized. Specifically to the pipeline that we've been looking at, we can easily speculate that the branch is not taken and just keep fetching the next instruction, and that doesn't cost us anything. Okay? So that is an easy road to take with our current pipeline. But realistically, again, that's not a realistic pipeline. So we need to talk about what are the techniques that are used in modern processors. And there are 2 types. A static branch prediction, in which we can look at the assembly language constructs that are used to implement specific high-level languages, structures, and predict the branch outcome based on the software, the typical software behavior of those high-level software constructs. For example, if we have a loop or if we have an if statement, then we can say we're going to predict that the branch is taken backward. That is the typical behavior of loops. Most of the time, you're going to be branching back in a loop until you complete the loop, then you keep going forward. But the loop normally is executed many times, so you can identify that a branch that is branching backwards in the code space belongs to the assembly language implementation of a for loop or a loop, and that the prediction of the branch being taken back is the way to go. And if a branch is branching forward, that is more typical of an if-else statement, in which the regular clause that you normally take, the path that you normally take is the if clause, not the else. So you can predict that the branch is not taken. That is the if clause. And in those cases, the branch is normally branching forward to the else part of the if-else. So you can predict that branches that are branching forward are not taken. So you can put hardware to identify those scenarios and use it as a way of statically predicting the branch behavior, because it's always going to be like that. Backward branches, you predict taken. Forward branches, you predict not taken. And you behave accordingly. And then if you are wrong, then you have to rewind your execution, flush the pipeline, stall, and restart fetching instructions from the right place in the code space. So that is the static branch prediction. A more sophisticated approach is what we would call dynamic branch prediction, in which you are actually monitoring in real time how much you are right or wrong in the way that you are predicting your branches, and then look at the history and the trend and modify your prediction. So again, we'll have hardware that measures the actual branch behavior and also the trend of the prediction, and modify adaptively that prediction accordingly. In other words, look at the trend and assume that the future is going to be like the recent trend, and that the trend is continuing. Again, at some point you're going to be wrong. When you are wrong, then you have to rewind, flush the pipeline, restart it, fetching from the right place, and then modify your history and your trend and start predicting again. So it's more complex, but it does tend to improve the statistics of your branch prediction. So we are going to go back to these topics, but for now, let's pause and review what we have seen so far. So we have seen so far that pipelining improves the performance by improving the throughput, the rate at which instructions are completed because we are executing multiple instructions at the same time. We're keeping all the stages, or attempting to keep all the stages, all the hardware of the implementation, the pipeline implementation, occupied. However, remember that each instruction still has the same latency. Each instruction is going to take 5 cycles, in our case, to complete. But the throughput is going to be improved, the rate of completion of instructions, which is, we don't care about a single instruction. We know that programs are made by huge streams of instructions, so the throughput becomes a real measure of performance. How soon can we complete and go through the stream of instructions? We also know that this type of approach is subject to hazards. We looked at structural hazards, data hazards, and control hazards. And one thing that we have been able to relatively easy address hazards in our Leg 8 implementation is the complexity of the ISA. It's a low complexity ISA that lends itself to easy implementations of hardware fixes to address hazards. So that is very important. Relating it back to the design and the decisions that we talked about when we were talking about the ISA architecture in chapter 2, it is very important to remember that the regularity of the instruction set, the characteristics of it such that we only have a handful of instructions that communicate with memory, that we have a large register file, that we have a regular instruction size and a pretty regular and minimal set of instruction formats and memory addressing modes, makes it easy for hardware solutions to improve the performance via pipelining and also addressing the hazards in hardware. So again, let's take another look at the 5 stages of our pipeline. We have what we call the IF stage, the instruction fetch. That's where we read the instruction from memory. The second stage is our instruction decode stage. That's where we read the source registers and generate the control signal, which is the decoding of the instruction. The act of decoding the instruction is generating the control signals to manage the next 3 stages to complete and effectively execute the instruction. So then we have the execution stage, in which we compute the R-type results here. We also compute the branch outcome, or we can compute the address for the load store type instructions. Then we have the memory stage, in which we read or write the data memory, given if it's one of those instructions, given the address that we computed in the execute stage. And then the last stage is what we call write back stage, in which we write the register. We write the register, the target register for either an R-type instruction, or we write the register for a load instruction with the data that we read from the memory in the memory stage. So those are our 5 pipeline stages for this implementation of the ARM processor that we're looking at. The similarities with the single cycle are important to highlight. because to come up with this pipeline implementation and pipeline that data path, you start with a single cycle that we already looked at. And you draw cut sets along that data path to see what is the best way to implement it and try to balance the hardware in the in each stage of the pipeline. Remember that you want to balance the delay, otherwise you degrade again to the single cycle performance. And we're trying to improve the performance over the single cycle from an instruction throughput perspective by a factor of 5, ideally, which is the number of pipeline stages. So if we look at the single cycle, looks very much like this, and now we are separating the pipeline stages, the 5 pipeline stages over here. A word of caution is that remember that when we talk about the processor, the memories are not part of the processor, even though we include them here as part for completeness and cohesion of the ideas that we're trying to talk about. This would be your instruction level 1 cache. This would be your data level 1 cache, and they are separate from the processor from a hierarchical and implementation perspective, a physical perspective. You can see on a chip clearly that the caches, even though they are next to the processor, they are not part of the processor. So it's important that we keep track of that. So let's that's our first cut into pipelining the ARM or the LEG V8 data path. And what we use to separate these stages are what is called pipeline registers. So in essence, these are registers that are going to isolate each stage from the next one. So whatever is coming out of this register are the Q outputs of the register, and over here we have the D inputs into the register. And in between two adjacent stages, we just have a register that is as long to capture as many things, as many items, as many signals as we need to, and save them there for the next stage. So we would need 4 pipeline registers to separate 5 pipeline stages. You can see them clearly. The IF, instruction fetch, instruction decode, execution, memory, and write back. So you can start seeing that by clocking these registers, everything that is between the registers is in essence combinational logic. So you have this systolic operation of cycle by cycle flow of instruction through the pipeline data path. So let's look at diagrams for, let's say, loads and stores, how they look through this data path. Here we have a load instruction. We are fetching the instruction with the contents of the program counter that, let's say, came from the previous program counter, and we just added 4 to it. And that's the next instruction, so we are going to fetch it. And at the end of that cycle, the instruction came, and then it got transferred from the output of the memory into, or the D of this register, into the Q, and now they are available for the next cycle. So The load now is being executed here while we are fetching the next instruction after the load. We don't know what that is, it's not shown here, but that's what we're doing here at the same time. Here, we are reading the register, and we are also passing and assign extending the label so we can then, in the next stage, calculate the address. The main thing here, the main factors here are the immediate field and register 1. So we are reading the register, decoding the instruction. We are not showing the control yet, but it's being the instruction is being decoded and the control is being generated. Then in the next stage, since we already know what the instruction is going to be, we know that is a load instruction, and we need to take the immediate label and the contents of register 1, and we need to calculate the address. That's what we do in the execution stage. And in the next cycle, we use that result as an address to read data. And now we have the data over here. And we do our data read in that memory stage for the load instruction. And then in the next cycle, we write that data back into the register. Now, hopefully, you were able to see that this is wrong, because that data that I'm writing over here, I'm writing it in a register. The address of this write register is not the address that I want to write to. That is coming from 1, 2, 3 instructions later. In other words, I'm not synchronizing the data with the write register address. So we need to fix that. So hopefully you were able to see that that's an issue. So we need to fix that. And we can fix that very easily by just sending the write register address, sending it through the pipeline from here, and having it come back synchronized with the data. So at that point, we do have the write register address. In essence, we saved it by keeping it going through the pipeline. So it went through the pipeline, through this path, and came back synchronized with the data. So that's an easy fix. But it highlights the issue that we have to keep data fields and addresses synchronized, because at any given time, what is being executed by any given stage of the pipeline is from different instructions. So now you can see that for the load instruction, now we fetch the register address here is not going into the register write register file port, is going down the pipeline. And then it comes back synchronized. So let's look at the store. For the store, we assume that we're just executing the very next instruction. We're doing our fetch of that store, and we're reading the register. We're computing the address. We're writing the memory. And then nothing happens during write back because the control never has to generate a write signal for the register file. All the control that we saw in the single cycle is still there. And the control looks very much like the single cycle control. So in essence, the pipeline implementation gives you the best of both worlds, which is the higher throughput, ideally an improvement of performance by a factor that is equal to the number of pipeline stages, but also the control is very simple. It is just like if you were decoding and controlling a single cycle, which is all combinational. You don't have to have a state machine to control a pipeline implementation. We'll see that what we do is we just send the control down from the decode stage, and the register, the pipeline registers act as state registers, passing the control down as is needed downstream for the other stages. So we'll go back to, we'll revisit that control, but it is important that you get used to the simplified diagram of a pipeline, which you can use to look at different clock stages and answer questions such as, what is happening at this specific clock cycle? It is important that you do that, and for that, we can look at simplified diagram of a pipeline, like the one shown here, where we have shaded essentially the resources that are used. So for the load instruction, we are fetching, we are reading the registers, we are computing the instruction, we are reading the memory, and we are writing the register. For subtraction or a register type, we are fetching the instruction, reading the register, executing the actual instruction, bypassing the memory, and writing the register, and so forth. So it is important to get in your mind, be able to draw this type of diagram quickly and be able to look at the sequence of instructions in terms of that diagram, so you can tell what is happening at a specific clock cycle. And it also allows you to identify hazard conditions. Another way is to do it this way, okay? But I think that the diagram is more, of course, more descriptive. Now let's look at a stream of instructions, okay? This over here would be the first instruction in the snippet or the code segment. The load, then the next instruction is a subtraction. The next one is an addition, then another load, then an addition. So this highlights the point that if I have this code sequence, when I am writing the contents of the memory as given by register 1 plus 40. When I'm writing that register 10, over here, what I'm doing is nothing. I'm bypassing the memory because that is a register type instruction. Here, I'm actually doing the addition of registers 4 and 3. Those are going to be the actual values at the input of the ALU, are the contents of registers 3 and 4. And what I have here is the result. At the same time, so all this is happening at the same time, in the same clock cycle. At the same time here, I'm reading register 1. So the contents of register 1 are sitting right here at the output of the port 1 of the register file. What I have here is the sign extended version of 48. And what I have here is the address of register 13, which I'm sending down the pipeline. So when I actually have the load into register 13 here, I capture the data synchronized with the right register address. And at the same time, in the same clock cycle, what I have here is that this instruction, add registers 6 and 5 and put the result in register 14, is sitting right here, right out of the memory. And here I have the program counter, because I need to send it down for the branch target address calculation. So it's important to understand that we have each stage is busy executing a different part of an instruction. So let's take another look at that. Look at this stream over here, which is the same one that we just went through. So we are fetching the load here. Now we are reading register 1 and sign extending 40, and we are reading this instruction. We are fetching this instruction in the second clock cycle. In the third clock cycle, now we are calculating the address for the load. Here we are reading registers 2 and 3, and we're fetching the addition. And now, during the fourth clock cycle, we are reading the data memory with the resulting address. We're actually doing the subtraction in the ALU here. We're reading registers 3 and 4 over here, and we are fetching this load instruction in the fourth clock cycle. And then on the fifth clock cycle, we are writing register 10 with what we got out of the memory in the resulting address. Here we're not doing anything, we're just bypassing the memory. Here we're doing the actual addition of registers 3 and 4. Here we are reading register 1 and sign extending 48. And here we are fetching this addition instruction, all at the same time during the same clock cycle. In the next clock cycle, now we are writing over here register 11 with the result of the subtraction. Again, here we're not doing anything, we're just bypassing the memory. Here we are computing the address for the load with the sign extended version of 48 and the contents of register 1. And here we are reading registers 5 and 6. Next, here we write register 12 with the result of the addition. Now we are accessing the memory for this load, so we are reading the memory, and the contents of the memory address, which comes from the contents of register 1 plus the displacement, the immediate displacement, is over here. And at this point over here, we are doing the addition of registers 5 and 6. And then in this clock cycle, we are writing the contents of the memory that we read in the previous clock cycle. We're writing it into register 13. Here we're bypassing the memory. And in the next clock cycle, that's when we write that result of the addition to register 14. So to wrap up, what we are going to be doing today is to, again, talk about the control. Notice that the control signals are the same as the single cycle. Exactly the same. For all the different multiplexers, for data steering, for the memories, read and write, for the ALU operation, that control, that subcontrol is the same. All we have to do is generate it, and we're going to generate it in this instruction decode stage and just send those signals down so they synchronize with the appropriate address, the appropriate instruction, which they're meaning to control. We're going to send it down the pipeline registers just like any other piece of information that we need to execute the instruction. So it becomes quite simple.